NENOMATICA, where mathematics meets YouTube excellence. Let's look at an example. Our polynomial is x to the fourth minus 10 x squared plus 9. First, we need to recognize that this is actually a quadratic in terms of x squared. We can rewrite it as open parenthesis x squared closed parenthesis squared plus negative 10 times open parenthesis x squared closed parenthesis plus 9. In the next step, we'll try to factor this expression. To do this, we need to break down the middle term negative 10x squared. We need to find two numbers that multiply to give 9 and add up to negative 10. Those numbers are negative 9 and negative 1. So we rewrite our expression as open parenthesis x squared closed parenthesis squared plus open parenthesis negative 9 minus 1 closed parenthesis times open parenthesis x squared closed parenthesis plus open parenthesis negative 9 closed parenthesis times open parenthesis negative 1 closed parenthesis. Now, we can apply the factoring pattern for a quadratic expression. The expression becomes open parenthesis x squared minus 1 closed parenthesis times open parenthesis x squared minus 9 closed parenthesis. Next, we notice that both x squared minus 1 and x squared minus 9 are difference of squares. We can factor them further. X squared minus 1 equals open parenthesis x minus 1 closed parenthesis times open parenthesis x plus 1 closed parenthesis. And x squared minus 9 equals open parenthesis x minus 3 closed parenthesis times open parenthesis x plus 3 closed parenthesis. So, our final answer is x to the fourth minus 10 x squared plus 9 equals open parenthesis x minus 1 closed parenthesis times open parenthesis x plus 1 closed parenthesis times open parenthesis x minus 3 closed parenthesis times open parenthesis x plus 3 closed parenthesis. We need to factor the expression x squared minus x, quantity squared, minus 8 times the quantity x squared minus x, plus 12. Let's work through this systematically. First, we'll use a substitution to simplify this expression. We'll let u equal x squared minus x, which will make our expression much clearer to work with. After substituting u equals x squared minus x, our expression becomes u squared minus 8u plus 12. This is now a quadratic expression in terms of u, which we can factor using the quadratic factoring method. Now we'll use the quadratic factoring method to factor this expression. We need to find two numbers that multiply to give 12 and add up to negative 8. The two numbers that multiply to 12 and add up to negative 8 are negative 2 and negative 6. So u squared minus 8u plus 12 can be factored as u minus 2 times u minus 6. Now we'll substitute back our original expression x squared minus x for u to get the factored form in terms of x. Substituting back u equals x squared minus x, we get the expression equals x squared minus x minus 2 times x squared minus x minus 6. Now, we need to factor each of these expressions further. Let's start with x squared minus x minus 2. We can use the quadratic formula or factoring by grouping to factor this expression. For the first expression, x squared minus x minus 2, we can factor it as x plus 1 times x minus 2. Similarly, for the second expression, x squared minus x minus 6, we can factor it as x plus 2 times x minus 3. Putting it all together, our original expression, x squared minus x squared minus 8 times x squared minus x plus 12 can be factored as x plus 1, x minus 2, x plus 2, x minus 3. Now, let's move on to our second example. Here we need to factor the expression a plus b squared minus 5a minus 5b plus 4. Similar to our first example, we'll use substitution to simplify this expression. Let's substitute u equals a plus b. After substituting u equals a plus b, we need to rewrite the original expression in terms of u. We can rewrite 5a plus 5b as 5 times a plus b, which is 5u. So our expression becomes u squared minus 5u plus 4. Now we have a quadratic expression in terms of u, which we can factor using the quadratic factoring method. We need to find two numbers that multiply to give 4 and add up to negative 5. The two numbers that multiply to 4 and add up to negative 5 are negative 1 and negative 4. So u squared minus 5u plus 4 can be factored as u minus 1 times u minus 4. Now we'll substitute back our original expression, a plus b for u, to get the factored form in terms of a and b. Substituting back u equals a plus b, we get the expression equals a plus b minus 1 times a plus b minus 4. Therefore, our original expression, a plus b squared minus 5a minus 5b plus 4, can be factored as a plus b minus 1 times a plus b minus 4. Let's start with our example. We need to factor the expression 2a squared times the quantity b squared plus c squared minus b squared times the quantity 2c squared plus b squared minus the quantity a to the fourth plus c to the fourth. The first step is to expand all the products in our expression. Let's apply the distributive property to each term. For the second step, we'll group the first 3 terms with negative a to the fourth and negative b to the fourth. This strategic grouping will help us recognize a pattern that can be factored. For the third step, we'll factor out a negative sign from the first group. This will help us identify a perfect square trinomial pattern. In the fourth step, we recognize that a to the fourth minus 2a squared b squared plus b to the fourth is actually a perfect square. It equals the quantity a squared minus b squared, all squared. For the fifth step, we'll factor out a negative sign from the entire expression. This allows us to bring all terms under one negative sign. In step 6, we notice that the expression inside the brackets is itself a perfect square pattern. It can be written as the quantity a squared minus b squared minus c squared, all squared. Finally, in step 7, we can simplify our expression by dropping the brackets on the square. Our final answer is negative times the quantity a squared minus b squared minus c squared, all squared. Today, we'll be factoring a complex expression step by step using algebraic techniques. Let's start by looking at our example. Let's solve this step by step. First, we need to organize our expression. The first step is to group the 4 linear terms into 2 quadratic expressions. We can group them as x plus 2 times x plus 5 in the first group and x plus 3 times x plus 4 in the second group. So our expression becomes the product of these 2 groups, minus 120. Now, let's expand each of these group products. For the first group, x plus 2 times x plus 5 gives us x squared plus 7x plus 10. And for the second group, x plus 3 times x plus 4 gives us x squared plus 7x plus 12. So our expression becomes x squared plus 7x plus 10 times x squared plus 7x plus 12 minus 120. Let's make an interesting observation. Both quadratic expressions have the same x squared and x terms x squared plus 7x. They only differ in their constant terms. So we can rewrite our expression as x squared plus 7x plus 10 times x squared plus 7x plus 12 minus 120. Light bulb tip. Recognizing common factors or patterns like this is key to solving complex algebraic problems efficiently. For the next step, let's use a substitution to simplify our work. We can think of x squared plus 7x as a single term. Let's call it a. So our expression becomes a plus 10 times a plus 12 minus 120. Now we can multiply these expressions using the formula a plus b times a plus c equals a squared plus b plus c, a plus b times c. So a plus 10 times a plus 12 equals a squared plus 22a plus 120. Substituting back a equals x squared plus 7x, we get x squared plus 7x, squared plus 22, x squared plus 7x, plus 120 minus 120. Now, we can see that we have plus 120 and minus 120 in our expression, which cancel out. So our expression simplifies to x squared plus 7x, squared plus 22, x squared plus 7x. Sparkle's note: always look for terms that can be combined or canceled to simplify your expressions. Looking at our expression now, we can see that both terms have a common factor of x squared plus 7x. Let's factor this out. We get x squared plus 7x times x squared plus 7x plus 22. Counterclockwise arrows button quick recap. We've grouped, expanded, recognized patterns, and are now factoring to simplify our expression. For our final step, we can factor the remaining common term. We know that x squared plus 7x can be factored as x times x plus 7. So our final factored expression is x times x plus 7 times x squared plus 7x plus 22. Party Popper, great job! We've successfully factored the complex expression. Let's summarize what we've learned. First, we grouped the 4 linear factors into 2 quadratic expressions. Then we expanded each group and noticed a common pattern. We rewrote the expressions to highlight the common terms. Using substitution, we simplified the multiplication. We canceled out terms that added to 0. We factored out common terms. And finally, we completed the factorization. This technique of grouping, recognizing patterns, and factoring is powerful for solving complex algebraic problems. Let's look at our example. We need to factor the expression x plus 1 times x plus 2 times x plus 3 times x plus 4 minus 24. Let's start with our step-by-step solution. First, we'll rearrange the expression to group the factors more effectively. We can rewrite this as x plus 1 times x plus 4 times x plus 2 times x plus 3 minus 24. This grouping will help us in the next steps of our factorization process. Now, we'll use brackets to group our factors. We'll group x plus 1 and x plus 4 in one bracket and x plus 2 and x plus 3 in another. So we have x plus 1, x plus 4 times x plus 2, x plus 3 minus 24. Let's now multiply the factors inside each group. First, we'll multiply x plus 1 and x plus 4. Using the FOIL method, first, outer, inner, last, we get x times x is x squared. X times 4 is 4x, 1 times x is x, and 1 times 4 is 4. So, x plus 1, x plus 4 equals x squared plus 5x plus 4. Similarly, we'll multiply x plus 2, and x plus 3x times x is x squared. X times 3 is 3x, 2 times x is 2x, and 2 times 3 is 6. So, x plus 2, x plus 3 equals x squared plus 5x plus 6. Therefore, our expression becomes x squared plus 5x plus 4 times x squared plus 5x plus 6 minus 24. Now, let's rewrite our expression in a different form. We can rewrite x squared plus 5x plus 4 as x squared plus 5x plus 4. And similarly, x squared plus 5x plus 6 as x squared plus 5x plus 6. This gives us x squared plus 5x plus 4 times x squared plus 5x plus 6 minus 24. Now, we'll multiply out these expressions. When we multiply x squared plus 5x plus 4 and x squared plus 5x plus 6, we get x squared plus 5x squared plus 10, x squared plus 5x plus 24. This simplifies to x squared plus 5x squared plus 10, x squared plus 5x plus 24 minus 24, which further simplifies to x squared plus 5x squared plus 10, x squared plus 5x. In this step, we'll factor out the common term, x squared plus 5x. From our expression, x squared plus 5x squared plus 10, x squared plus 5x, we can factor out x squared plus 5x to get x squared plus 5x times x squared plus 5x plus 10. For our final factorization step, we'll factor x squared plus 5x as x times x plus 5. This gives us x times x plus 5 times x squared plus 5x plus 10. Now for our final answer, we can simplify this further. We notice that the final factor, x squared plus 5x plus 10, can be factored as x plus 5 times x plus 2. So our completely factored expression is x times x plus 5 times x plus 5 times x plus 2, which simplifies to x times x plus 5 squared times x plus 2. Let's start with our example. Let's begin by grouping our terms in a way that will help us identify patterns. We notice that x squared, 4y squared, and negative 4xy can be grouped together to form a perfect square trinomial. Let's also group the terms with single variables, negative 5x and positive 10y, and keep the constant negative 24 separate. In the first group, we recognize the pattern x squared minus 4xy plus 4y squared. This is a perfect square trinomial that can be written as the square of x minus 2y. We can rewrite the entire expression using this perfect square. Now, let's look at the linear term, negative 5 times x minus 2y. We need to split this coefficient negative 5 into 2 parts that will help us factor the expression. We can write negative 5 as negative 8 plus 3. This specific split is chosen because the product of negative 8 and 3 is negative 24, which is our constant term. Let's rewrite the expression using this split. We've now set up our expression in a form that matches the pattern a squared plus n times a plus m times n, which factors as a plus m times a plus n. In our case, a is x minus 2y, m is negative 8, and n is 3. Let's apply this factoring formula to complete our solution. Therefore, our factorized expression is x minus 2y minus 8 times x minus 2y plus 3. This is our final answer. Let's look at our example problem. We need to factor the expression x plus 1 times x plus 3 times x plus 7 times x plus 5 plus 15. Let's solve this step by step. Our first strategy is to group the factors to make our work more manageable. We'll start by grouping the first two factors and the last two factors. Now, we'll expand each of these group terms. Let's use the FOIL method to expand the group terms. Next, let's regroup the terms to make our next steps clearer. We'll factor out common terms inside each group. Now, we'll multiply these expressions using the distributive property. Let's apply the distributive property to expand the product. Let's continue simplifying our expression. We'll factor the expression to get a perfect square trinomial form. Now, we'll apply the difference of squares formula to factor our expression. The difference of squares formula allows us to factor a squared minus b squared as a plus b squared as a plus b times a minus b. Let's simplify the terms inside each parenthesis. Now, we'll factor each of these quadratic expressions. We need to find factors of 12 and 10 that add up to 8 for each expression. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.